Hi, and welcome to this video on potential energy. We are going to be finding the potential energy from different forces today. And to really understand how to find the potential energy from forces, we are going to have to utilize a little bit of calculus and specifically utilize integration. We'll get more to why in a second. But before we do that, let's jump into a little bit of a calculus review. So the type of calculus we will be doing today is integration, and we will be specifically looking at integration of powers. So let's say x to the n dx. Well, the integral of x to the n dx is relatively straightforward. What do? We first increase the power of n by 1, and we divide that by the new power, n plus 1. And then we evaluate this over its limits. We evaluate it from initial to final. And that's how you would find this integral. As an example, let's say we have a value of 1 over x squared, right? Let's say we want to know what the integral of 1 over x squared dx is. Well, this can be rewritten as the integral of x to the negative 2 dx. And what do? We first increase the exponent by 1. So that's going to be x to the negative 1. And then we divide by that new exponent, divide by negative 1. And this can be rewritten as negative x to the negative 1, right? We just take the negative out front, or negative 1 over x. What if we were to ask for what the integral of x dx is? Well, x can be rewritten as x to the first power dx. And when we take a look at this, we say we raise the exponent by 1, so it's going to be x squared. And then we divide this by 2, and that would be 2x squared. So that's the calculus we're going to be needing today. Not too bad, right? It's all stuff that we've probably seen before. But these are the various integrals that we're going to be looking at. Now we're going to look at two forces, but one of the forces we're actually going to take a look at two ways. We're going to start off with gravity. And yes, we've already looked at gravity, but we'll be a little more specific here, right? So when we look at gravity, we know the force of gravity is equal to mg. As long as you're near the Earth's surface, this is true. We know that the change in potential energy for an object, well, the change in potential energy is going to be equal to the negative of the work done. Work is defined to be the integral of force dx. And yeah, I know we've been using force times displacement. This is just another way to write force times displacement, where you take displacement to be a very, very tiny split displacement dx, and we sum together all of those infinitesimally small dx works caused by those little dx's over time, to give us the total work done. So what this leads us to is that the change in potential energy is equal to the negative integral f dx, and that's what we'll be using today. With gravity, we can say that an object near the Earth's surface would have a force equal to the object's mass times acceleration due to gravity. And then we put our dx in here. But what do we know? We know objects don't typically change in mass, so that's a constant. We can pull that out of the integral. Delta U is equal to negative m integral g dx. And that g value, well, as long as you stay near the Earth's surface, g is a constant as well, 9.8 meters per second squared. So we pull that out of the integral as well, and you get negative mg integral dx. And, well, the integral of dx is easy. Integral of dx is just delta x. Negative mg delta x. Where in this case, delta x, yes, we're using x here instead of y, but bear with me here. If we define x to be our displacement, delta x would be our vertical displacement here, because gravity only does work when we have vertical displacement, meaning our potential energy only changes when we have vertical displacement. So this gives us our potential energy due to gravity. Now, I said we're going to look at gravitational forces two different ways. The other way we are going to look at it is the more universal sense, right? we look at universal gravitation. And if you remember, universal gravitation is defined by the force of gravity equaling the gravitational constant, this 6.67 times 10 to the minus 11 newton meters squared per kilogram squared. And we take this gravitational constant, we multiply it by the masses of the two objects which are interacting through gravity, and we divide it by the distance between their centers squared. So if we take two objects, mass 1 and mass 2, maybe these are two planets or a planet and its moon, and we look at these two planets as having some distance x between them, we can define their force as being g m1 m2 over distance x squared. And then we ask, well, what is the potential energy between them? We've discovered gravitation is one of these conservative forces, so there should be potential energy between them. The potential energy is equal to the negative of the work. We describe that as integral f dx. Well, we know what the force is, g m1 m2 over x squared dx. Our gravitational constant, mass and mass of objects 1 and 2, those are all constants. So we say this is equal to negative, we pull those constants out of the integral, g m1 m2. We have the integral of 1 over x squared dx, and what do you know? We looked at that just a few minutes ago. And we know that that should equal negative 1 over x. So what does this give us? It gives us negative g m1 m2, and the integral solves to negative 1 over x. Well, the negatives will cancel each other out. We can put this in fraction form, and we end up with g m1 m2 over x as our gravitational potential energy. And this is the universal case. If we were to ask how does this reduce down to the value that we've found earlier, well, we would just take x to be the radius of the Earth, m1 to be the mass of the Earth, and then we have our g times m times delta h. And this gives us our change in gravitational potential energy more universally. All right, well, what was the third case, right? I said we're going to look at 3 different forces. These 3 different forces give us 3 different potential energies. The third force is going to be from a spring. And if we look at a spring, we can imagine a spring on a table where we stretch it some distance delta x, put a mass on it. So here we stretch our spring a distance x, and we ask, well, what is the force on this spring? The force on this spring is given by Hooke's law, and we can write that as negative k times x. That negative sign means that we are in the opposite direction of our displacement. Well, the work here would be defined by, yes, the the integral of f dx, but we also need in here a cosine of theta. I left this out earlier because in the earlier versions, the displacement, we're saying displacement in the same direction. We're kind of negating this, but it is important, especially here. So when we look at this cosine theta, that is the angle between our displacement and our force. Here we've displaced our object to the right, a distance delta x. Our force from our spring is to the left, meaning theta is equal to 180 degrees. So the work done here would be negative integral of the force's magnitude, kx, dx. So remember here we're looking at magnitude of force, magnitude of displacement. All right, well, the change in potential energy, which is the negative of the work, must be equal to, well, negative of negative integral kx dx. The negatives cancel out. The change in potential energy is equal to the integral kx dx. K is a constant. Since it is a constant, we can pull it out of the integral. We end up with x dx. And what do you know? This is the other integral that we saw earlier. And we found that the integral here solves to x squared over 2. So delta u is equal to spring constant k multiplied by x squared over 2. And we actually usually write this as 1/2 kx squared. This is actually a result that we found earlier when we looked at the work done by a spring. But here it is, utilizing calculus method to give you your delta U. And what can we take away from this? Well, we can take away from this that the change in potential energy from any force that you're given can be found with the negative integral of the strength of that force multiplied by the displacement dx multiplied by the cosine of the angle between that force and the direction of travel. This is going to be generally true. All right, so there you have it. The forces that are non-constant that we've seen, how do they give us potential energies, or how can we calculate those potential energies? We just utilize a little calculus. We just do some integration. All right, if you have any questions about this, please let me know. Otherwise, I'll see you next time.